Welcome to Talk Tensors. I want to start today by asking you to, picture a scenario.
Okay, I'm picturing it.
So it's the early 2010s, right? You are in your car, you're driving down the highway, and you decide to use the cutting-edge voice assistant on your brand new smartphone.
Oh boy, I know where this is going.
Yeah, you press the button, the little microphone icon pops up, and you say very clearly, "Call mom."
Right.
You wait a second. The phone thinks about it.
Right.
And then a cheerful robotic voice replies, "Calling Tom."
Mm-hmm. Classic.
You sigh, you cancel it, and you try again. You over-enunciate, "Call mom." And the phone says, "Navigating to the Taj Mahal."
It was incredibly frustrating. I mean, it happened constantly.
Constantly. And we just sort of accepted it, you know? We accepted that unless you were in a completely silent room speaking with the rigid cadence of a news anchor, speech recognition software was basically a roll of the dice.
It really was.
But the crazy thing is, it wasn't for lack of trying. I mean, computer scientists have been working on speech recognition for decades.
Oh, absolutely. Decades of really intense research.
So before we get to the actual breakthrough that we're covering in this deep dive today, I want to understand what was going wrong in those early systems. Why were they so uniquely terrible at understanding human voices the second there was just a little bit of background noise?
Well, to understand why they failed, you really have to look at how they were built. The classic approach to automatic speech recognition, or ASR, was essentially a towering stack of hand-engineered parts.
Like a fragile tower.
Exactly. It was the absolute definition of a Rube Goldberg machine. Researchers treated speech not as a fluid stream of data, but as this rigid linguistic puzzle that had to be solved in very specific, discrete steps.
Okay, so walk me through that puzzle. If I speak into a microphone in, say, 2010, what exactly is the computer doing behind the scenes?
First, the audio wave hits the microphone. But the computer doesn't just look at that raw audio wave.
Right, it has to translate it.
Yeah, it runs it through a specialized feature extractor. And for decades, the gold standard for this was something called MFCCs, or Mel Frequency Substral Coefficients.
Wow. That is a very intimidating string of words. What does a Mel Frequency Substral Coefficients actually do?
It's actually a fascinating piece of biomimicry, honestly. The scientists who developed MFCCs looked at the human ear, specifically the cochlea, because our ears do not hear all frequencies equally. We are highly sensitive to small changes in low pitches, but we are terrible at distinguishing between two very high pitches.
That's what I didn't know that.
Yeah, so researchers wrote complex math to warp the digital audio signal to mimic the human ear's physical limitations. They literally built a digital cochlear.
That's wild.
Right. It squashes the high frequencies and highlights the lower ones where human speech usually lives.
That sounds incredibly clever, though.
Yeah.
If we're trying to understand human speech, why wouldn't we want to process sound the way a human ear does?
Because it is a lossy process. By forcing the computer to mimic human biological limitations, you are intentionally throwing away massive amounts of acoustic data.
Oh.
Yeah, you are throwing away the high frequencies. Now, if you are in a quiet room, that's fine. But what if you are in a car and the wind is howling and the tires are humming on the asphalt?
Ah, I see. A lot of that noise might exist in the frequencies we just threw away.
Precisely. And if you throw away the data that contains the noise, you can't subtract it. The system becomes blind or deaf, rather, to the environment.
It can't adapt to what it can't hear.
Exactly. But that was only step one. After the MFCCs mangled the audio, that data was fed into an acoustic model, which tried to guess the basic sounds.
Okay.
Then that output was fed into a hidden Markov model, or H&M.
I've heard of hidden Markov models. They're basically probability engines, right?
Essentially, yes.
Well,
in this context, an H&M is looking at a sequence of sounds and trying to calculate the probability of moving from one state to another.
like guessing the next letter.
Kind of. It's saying, given that I just heard a K sound, what is the probability that the next sound is an A? But to do this, the H&M required an incredibly dense, handwritten phoneme dictionary.
A phone dictionary.
Yeah.
So a team of linguists literally had to sit down and map out every single phonetic sound in the English language.
Exactly. Phones are the distinct units of sound that distinguish one word from another. The P in pat versus the B in back.
Right.
Linguists had to painstakingly write rules dictating how every word in the dictionary broke down into these phonemes.
Man, so you have a digital cochlea throwing away data, feeding into a probability machine, which is cross-referencing a rule book written by human linguists.
You got it.
I'm starting to see why my phone thought I wanted to go to the Taj Mahal. If any one of those brittle hand-tuned components breaks down because, I don't know, a dog barked in the background, the whole pipeline collapses.
It was a towering inferno of linguistic rules, and deep learning neural networks were barely involved.
Really? Even back then?
Barely. Maybe a team would train a small neural net just to optimize the acoustic model, but they wouldn't dare touch the phone dictionary or the HMM. Those were sacred.
Untouchable.
Yeah, deep learning was just a tiny patch on a massive, leaky ship.
Which brings us perfectly to the focus of today's deep dive. We are looking at a truly seminal paper in the history of machine learning that decided to stop patching the ship and instead just build a completely different kind of boat.
A completely new paradigm.
Exactly. The paper is titled Deep Speech, Scaling Up End-to-End Speech Recognition. This was published by Ani Henon, Andrew Y.N., and the Baidu Research Silicon Valley AI Lab. And just a quick reminder to you listening, the link to the full paper is right down in the bio.
It is a phenomenal piece of work to revisit. It marks a distinct shift in how we approach not just audio, but complex, noisy data in general.
So let me state the core premise, like the thesis of what we are going to unpack today. This paper proved that by abandoning decades of hand-engineered linguistic pipelines and instead scaling up a simple recurrent neural network with massive data and clever GPU parallelization, end-to-end deep learning could achieve state-of-the-art speech recognition, even in highly noisy environments.
That is the perfect distillation of their achievement. They didn't try to build a smarter linguistic rule.
Right.
They realized that a sufficiently large neural network fed enough raw data could simply learn the rules of human language on its own.
Let's dive right into that philosophy because this is a massive shift. In traditional ASR, as we just discussed, the system is deeply dependent on phones.
Yeah.
It has to know the phonetic building blocks.
Yes.
But deep speech proposed something radical. Erase the phoneme. The system proposed here maps raw audio directly to English characters.
Directly to the alphabet.
Yeah. It just outputs A, B, C, D, space, apostrophe. It has zero concept of what a phoneme even is.
And that choice is the exact reason it succeeds where other models failed. Well, if you rely on phonemes, you are forcing the computer to conform to a human construct. Phonemes are how we categorize sound to make it easier to teach in, like, elementary school.
Right, sounding things out.
Exactly. But sound waves in the real world do not care about elementary school phonics.
They're just physics. Vibrations in the air.
Exactly. When you speak, you don't actually output discrete, perfectly separated phonemes. The end of one word slurs into the beginning of the next.
That makes sense.
Your vocal cords are in continuous motion. If a system is forced to chop that continuous physics into rigid linguistic boxes, it will fail when the audio gets messy.
Because the boxes don't fit the mess.
Right. By bypassing the foam entirely, an end-to-end system internalizes the robustness automatically. It learns what speech sounds like through the noise, rather than trying to perfectly isolate a phonetic rule.
The analogy I keep coming back to is this traditional ASR is like a committee of rigid academic linguists sitting around a mahogany table.
I love this.
They're listening to a grainy, static-filled audio tape. And they're arguing. Well, according to Section 4 of the dictionary, that high-pitched burst is clearly a fricative, so it must be this specific phoneme, which means the word is this.
Very bureaucratic.
Right. They're overthinking it, getting bogged down in their own bureaucratic rules. Deep speech, on the other hand, is like a savant. It sits in a room alone, listens to 1,000,000 hours of raw audio, and intuitively maps the physics of the sound directly to the letters on a page.
It just knows.
Yeah, it doesn't know the rules of grammar, it just feels the pattern.
That's a great way to visualize it. The savant doesn't need to explain its reasoning, it just produces the correct output based on overwhelming experience.
But I do want to challenge this a bit. Looking back from today, it seems obvious, but at the time, wasn't tossing out decades of linguistic theory a huge gamble?
Oh, absolutely.
Like, how did the Baidu team know a neural network could capture all that complex human language structure without us holding its hand? I mean, humans spent centuries mapping out linguistics. Throwing it away almost feels arrogant.
To the traditional linguistics community at the time, it absolutely felt arrogant. There was massive resistance.
I bet.
You have to remember, throwing away phonemes felt like trying to teach a computer to read a novel without first teaching it the alphabet. It felt completely counterintuitive.
Right, you have to walk before you can run.
Exactly. But it wasn't arrogance from the researchers. It was a profound trust in the mechanics of deep learning. They hypothesized that if the architecture of the network is correct and the volume of data is vast enough, the network will implicitly build its own internal representation of language.
And did it?
It did. And here's the kicker. The internal, unreadable representation that the neural network invents might actually be far more robust and nuanced than the rigid, simplified phonemes that humans try to write down.
Wow.
The computer finds the actual mathematical boundaries of the sound, not the human perceived ones.
Okay. That is a profound thought. We're basically admitting that our human categorization of language is too simplistic for a machine to use in the real world.
Yeah, pretty much.
So we let the machine invent its own categorization, which naturally brings us to the machine itself. Let's look at the actual architecture of deep speech. How is this savant structured?
The overarching theme of the architecture is simplicity over complexity. Compared to the convoluted pipelines it replaced, the deep speech network is shockingly straightforward.
Okay.
It consists of exactly 5 hidden layers.
Let's walk through it step by step. First, the input. What exactly are we feeding this network? We aren't just feeding it raw MP3 files, right?
Not quite raw audio, no. They feed the network spectrograms.
I know a spectrogram is a visual representation of sound, but
Yeah.
Explain what the network is actually seeing mathematically.
Imagine taking a sound wave and passing it through a prism.
Like Pink Floyd.
Exactly like that. Just like a prism splits white light into a rainbow of distinct colors, a mathematical process called a Fourier transform splits a complex sound wave into its distinct frequency components. A spectrogram plots this over time. The horizontal axis is time, moving forward in tiny increments of milliseconds. The vertical axis is the frequency, the pitch of the sound, from low bass to high treble.
Got it.
And the color or intensity of the plot represents the power or volume of that specific frequency at that specific millisecond.
So it's essentially a topographical map of the sound. You can see the mountains of loud, high-pitched sounds and the valleys of quiet moments.
Perfectly put. It's a 2D matrix of numbers representing power and frequency over time. Now, the network doesn't just look at one single millisecond slice of this map at a time. It uses a context window.
A context window.
Yeah. For every time step, it looks at the current frame of audio, plus the 9 frames immediately preceding it, and the 9 frames immediately following it.
Why the window? Why not just process it exactly as it happens?
Because sound in isolation is meaningless. Think about a plosive sound like the P in pop.
Okay, a P sound.
The sound itself is just a burst of air. To know if that burst is a P or a B or just a microphone pop, you need to see what the frequencies were doing immediately before the burst and what they do immediately after.
Yeah, I see.
The context window gives the network temporal awareness. It lets it see the trajectory of the sound.
Okay, so we have this sliding window moving across our topographical map of sound. Where does that data go first?
It feeds into the first 3 layers of the neural network. These are non-recurrent layers.
Meaning what?
Meaning they process the data in a straight line feed-forward style. The data goes in, gets multiplied by some weights, and passes through an activation function.
Now, the paper specifically states they use a clipped rectified linear unit, or a clipped ReLU. And they explicitly mention they cap this ReLU at a value of 20.
Yes, the cap is crucial.
I want to linger on this because a standard ReLU just lets positive numbers pass through unchanged and turns negative numbers to 0. It's a very basic filter. Why did they feel the need to cap it at 20? Like, what happens if a number hits 21?
This gets to one of the most notoriously frustrating problems in training deep neural networks, especially ones that deal with sequences of time. It's called the exploding gradient problem.
Okay, unpack that for me. What is exploding?
When you train a neural network, you are constantly making tiny adjustments to the weights of the connections based on how wrong the network's guess was.
Right, that's learning.
Yeah. This process, backpropagation, involves calculating derivatives. Essentially, multiplying a long chain of numbers together across all the layers of the network.
Okay.
Now think about basic math. If you take a number slightly smaller than 1, say 0.9, and you multiply it by itself 100 times, it shrinks down to practically 0. The signal vanishes.
Right, but if you take a number slightly larger than 1, say 1.1.
Exactly. If you multiply 1.1 by itself 100 times, it grows exponentially. It explodes.
Right.
In a deep network, if the activation values are allowed to grow unchecked, these multiplication chains can suddenly produce mathematically massive numbers. The gradients explode.
And what happens then?
The network's weights get updated with completely absurd values, and the entire model essentially blows up and forgets everything it learned. it destabilizes.
So capping the ReLU at 20 is basically installing a circuit breaker.
It is exactly a circuit breaker. It puts a hard mathematical speed limit on the activations. It says, I don't care how strong the signal is, you are not allowed to pass a value higher than 20 to the next layer.
That's smart.
It keeps the math stable, preventing the snowball effect during training.
So we pass through these 3 feed-forward layers, clipping the signal so it doesn't melt down. Then we hit layer 4, and this is the engine of the whole operation. Layer 4 is a bidirectional recurrent layer.
This is where the magic happens. A standard recurrent neural network, or RNN, has a loop. It looks at the current data, but it also maintains a memory state from the previous time step.
So it remembers the past.
Right. It reads the data sequentially from left to right, just like we read a book.
But this one is bidirectional, meaning it's reading backward at the same time.
Yes. It actually has 2 independent sets of hidden units. One set reads the spectrogram forward in time, from the first second of audio to the last.
And the other?
The other set reads the exact same spectrogram, but it starts at the end of the audio and reads backward to the beginning.
This makes so much intuitive sense when you think about how human language works. If you are trying to decipher a muffled word I just said, the best clue you have is the word I'm about to say next.
Exactly.
Context flows in both directions. If I say the bark of the muffled sound was rough, the missing word is tree because of bark and rough.
Yes.
But if you only read left to right, you might hear the bark of and think I'm talking about a dog.
That is a brilliant example. Human language is entirely dependent on backward and forward context. The bidirectional layer allows the network to have a complete view of the utterance before it commits to guessing what a specific sound is.
Now, in the paper, they present the mathematical equation for this layer. I know we aren't going to read the Greek alphabet soup aloud, but I want to understand the conceptual geometry of it. How exactly does the network combine the present and the past?
The math looks intimidating on paper, but conceptually it's very elegant. Imagine the forward reading part of layer 4. At any given millisecond, it needs to generate a new internal thought, a new state. To do this, it takes 2 distinct inputs. First, it looks down at layer 3. It takes the freshly processed audio features coming up from below.
From the feed-forward layers.
Right. Second, it looks back at itself. It takes the memory state it generated just 1 millisecond ago.
So it adds them together.
It multiplies both of those inputs by their respective weights, which the network learns during training, adds them together, adds a small bias number, and then shoves that entire combined sum through our trusty clipped ReLU circuit breaker.
So, simply put, its current thought is a combination of what it is hearing right now plus what it was thinking a fraction of a second ago.
Exactly. And the backward reading in it is doing the exact same mathematical operation, just sliding from the future into the past.
Which brings us to layer 5 and layer 6. Layer 5 is another simple feed-forward layer. I assume its job is just to stitch the forward and backward thoughts together?
That's precisely its job. It takes the output from the forward RNN and the output from the backward RNN, combines them, and creates a unified representation of that specific moment in time, fully contextualized by both the past and the future.
And finally, layer 6, the output layer. It uses a standard softmax function, so it's basically just spitting out probabilities.
Yes. For every single time step, which is incredibly fast, just fractions of a second, layer 6 looks at that unified representation and spits out a probability distribution across the English alphabet.
So it's guessing the letter.
Right. It says, this exact millisecond, I am 80% sure this sound is the letter S, 10% sure it's a C, and 10% sure it's a Z.
Okay.
It has an output for all 26 letters, a space character, an apostrophe, and one very special, crucial token, the blank token.
Okay, I have a massive elephant in the room I need to address before we talk about that blank token. I am looking at this entire architecture. Spectrogram in. 3 feed-forward layers with basic ReLUs. 1 bidirectional recurrent layer. 2 more feed-forward layers. Probability out. I am scanning this paper, and I realize something is missing. Where are the LSTMs?
I was waiting for you to catch that.
At the time this paper was published, long short-term memory units, LSTMs, were the undisputed kings of sequence modeling. If you're doing anything with text, audio, or video, you used an LSTM because they were specifically designed to solve that exploding and vanishing gradient problem we talked about earlier.
Yes, they were the standard.
They are incredibly smart memory cells.
Yeah.
Why on earth did the Baidu team build a state-of-the-art model in 2014 using basic ReLUs instead of LSTMs?
This is one of my favorite aspects of the paper because it highlights the difference between theoretical computer science and applied engineering.
Okay, explain that.
LSTMs are mathematically brilliant. They have internal gates, an input gate, a forget gate, an output gate. They can meticulously decide what information to keep and what to throw away over long periods of time.
Sounds perfect for speech.
It is, theoretically. But that mathematical brilliance comes with a massive cost. Compute.
Because every single gate requires its own set of matrix multiplications.
Exactly. Computing an LSTM cell requires a massive amount of math. And here is the fatal flaw for speed. Recurrence is sequential.
Right, you can't parallelize time.
You cannot compute time step 2 until you have completely finished computing time step 1. You cannot parallelize the flow of time.
Oh, I see. So if the cell itself is slow, you have to do them one by one, millions of times, the whole network crawls to a halt.
Precisely. The Baidu team realized that LSTMs were a massive computational bottleneck. They made a brilliant contrarian trade-off.
Which was?
By abandoning LSTMs and reverting to a highly simplified homogeneous model using basic ReLUs, they traded theoretical complexity for raw speed. Computing a basic ReLU is incredibly cheap.
Because it's just 0 or the number.
Right. It requires just a few highly optimized BLAs operations, basic linear algebra subprograms running directly on the GPU.
They essentially looked at the problem and said, we don't need a smarter mathematical cell. We just need a vastly faster one, because if it's faster, we can push 10 times more data through it.
More data beats a smarter algorithm. It is the recurring mantra of deep learning. They used a blunt instrument, but they swung it with incredible speed.
That is fascinating. But it brings us to another bottleneck. The training process itself.
Yes, the alignment problem.
Right, because we have this lightning-fast network outputting probabilities for letters every few milliseconds. But how does it know if it's right? How do you calculate the error, the loss, to train it?
It's a huge challenge.
Because if I give the network a 10-second audio clip of me saying, hello world, the network outputs thousands of letter predictions across those 10 seconds. How does it map those thousands of predictions back to the 10 letters in hello world?
You've just described the alignment problem, which was the absolute bane of early speech recognition research.
How did they used to do it?
In the old days, researchers had to manually align the text with the audio. A poor grad student had to sit with audio software and manually tag, the H sound starts at 0.12 seconds and ends at 0.28 seconds. The E sound starts at 0.28 seconds.
That sounds like actual torture. You couldn't possibly do that for thousands of hours of data.
You can't. So deep speech utilizes a brilliant mathematical solution called Connectionist Temporal Classification, or CTC loss. CTC is magic. It completely eliminates the need for manual alignment.
How? If I say hello world slowly, the L sound might last for a full second. The network is spitting out predictions every few milliseconds, so it might output HELLLLLO. How does CTC know that a block of 20 L's just means one single L in the final spelling?
This is where that special blank token comes in that we mentioned earlier. The network isn't just predicting letters, it's predicting the space between sounds. The CTC algorithm uses a clever set of rules to collapse repeating characters unless they are separated by a blank.
So if the network outputs HELLL blank LOO, CTC collapses that down to HELLO.
Yes, the blank acts as a delimiter.
So if it predicts 20 L's in a row, it just assumes I held the sound and squashes it to one L. But if it predicts L, then a blank, then another L, it knows it's a double consonant.
Exactly. And during training, the CTC algorithm looks at the raw audio, looks at the target text hello world, and internally calculates the probability of every single possible valid alignment of that text across the audio's time frame.
Wow.
It sums up all those probabilities to calculate one final error score. The beauty is you just feed it the raw audio file in the final transcript. The CTC math figures out the internal timing automatically.
Okay, so let's take a breath and survey where we are. We have an incredibly lean, simple architecture using fast ReLUs. We have CTC loss automatically handling the messy timing alignments. The software is optimized.
It's a great setup.
But having a fast network on paper means absolutely nothing if you can't push the data through the physical hardware efficiently. The unrolled network they are describing has almost 5 billion connections per utterance. Training this in 2014 required what I can only describe as aggressive, almost violent optimization of the physical hardware.
Violent optimization is highly accurate. Let's look at what they had to do to tame the hardware.
Please do.
They knew they needed to process massive amounts of data simultaneously to finish training in our lifetime. This meant utilizing data parallelism. They needed to feed massive mini batches of audio across multiple GPUs at the exact same time.
But there's an immediate logistical problem there. Audio clips are not uniform. You have a 2-second clip of someone saying yes and a 15-second clip of someone telling a story.
Right.
You can't just shove those into the same matrix multiplication block easily.
Right.
GPUs are essentially massive math factories, and they love rectangles. They love perfectly uniform, predictable grids of numbers. They hate jagged, uneven data.
Exactly. If you send a GPU a jagged array of data, it has to constantly stop, reallocate memory, and figure out what to do with the empty space. It kills efficiency.
So what did they do?
The Baidu team had to hack the data structure. First, they sorted their entire training dataset by length. They grouped utterances that were almost the exact same duration together.
Okay, so a batch of 5-second clips, a batch of 8-second clips.
Right. But even then, they aren't identical to the millisecond. So they padded the tiny differences with silence.
Just dead air.
Yeah. If one clip was 5.1 seconds and another was 5.3 seconds, they just added 0.2 seconds of digital silence to the first one. By doing this, they constructed these massive, perfectly rectangular mini batches.
That's smart.
And they utilized concepts from sparse matrix formats to ensure the GPU only performed math on the actual audio, not the padded silence.
So they smoothed out the data so the GPUs could just hum along without thinking. But that only solves getting the data into the machine.
What about the model itself? We said it has 5 billion connections. In 2014, GPU memory was tiny compared to today.
You cannot fit a 5 billion connection recurrent network onto a single graphics card.
No, you absolutely cannot. It would immediately crash with an out-of-memory error. This is where model parallelism comes in. They had to slice the actual neural network in half and put half on one GPU and half on another.
But wait. We just talked about how layer 4 is recurrent. It depends on the flow of time. If you slice the model and put the forward pass on GPU 1 and the backward pass on GPU 2, you have a massive physical problem.
And what's that?
When it's time to combine those thoughts, at layer 5, GPU 1 and GPU 2 have to send their data to each other. They have to transmit gigabytes of intermediate math across the motherboard's PCIe bus.
And the PCIe bus is painfully slow compared to the internal memory of a GPU. If they did that, the data transfer bottleneck would completely erase all the speed gains of using ReLUs. Data transfer is the ultimate enemy of speed in deep learning.
So how did they slice it without causing a traffic jam on the motherboard?
They didn't slice it by layer, they sliced it along the time dimension.
Oh, I love this part of the paper. I've been trying to come up with an analogy for this. Tell me if this tracks.
Let's hear it.
It's like they have been contracted to dig a train tunnel straight through a massive mountain. The naive approach is to have one massive digging machine start at the west entrance and dig all the way to the east. But that takes too long.
Way too long.
So they split the team. Digging machine 1 GPU 1 starts at the west entrance, digging forward into the mountain, which represents the first half of the audio file. Digging machine 2 GPU 2 starts at the east entrance, digging backward into the mountain, representing the second half of the audio file.
That is exactly what they did. Let's look at the precise mechanics of that midpoint swap. GPU 1 is churning away, computing the forward pass from the start of the audio, time $2.1, moving forward until it hits the exact mathematical midpoint of the audio. Let's call it TTT to the audio 2.
Right, the center of the mountain.
At the exact same time, GPU 2 is computing the backward pass. It starts at the very end of the audio, $2, and computes backward until it hits that exact same midpoint, $2T2.
And when they finally meet in the middle of the mountain,
they exchange their blueprints. At that specific midpoint, they perform one single synchronized data transfer across the motherboard. GPU 1 hands GPU 2 the forward-flowing context it just generated. GPU 2 hands GPU 1 the backward-flowing context it just generated.
They literally swap roles.
They do. Then GPU 1 uses that new backward context to finish digging to the start of the audio, and GPU 2 uses the forward context to finish digging to the end of the audio.
That is just gorgeous engineering. They constrain the massive data transfer penalty to one single moment in the middle of the process. For the entire rest of the computation, the GPUs operate in total isolation at maximum speed. They just pass the baton and keep running.
It's brilliant. And they added one more architectural trick to squeeze out speed right at the beginning of the network: striding.
I noticed that. What does striding do in this context?
In that very first non-recurrent layer, the one looking at the spectrogram, they didn't process every single frame sequentially. They took steps of size 2.
Skipping frames.
Yeah, they processed a frame, skipped one, processed the next. It acts somewhat like a convolutional neural network, or CNN. By striding by 2, they instantly halved the total number of time steps that the unrolled recurrent network had to process.
Yeah.
It effectively compressed the time dimension by 50% without losing the broader acoustic context. And they implemented this using highly optimized custom code from the cuDNN library.
Okay, let's take a step back. The hardware is meticulously optimized. The data is batched into perfect rectangles. The GPUs are humming along, passing batons, digging tunnels from both sides. The architecture is lean and mean.
It's a powerhouse.
Right. They built an engine that can digest anything thrown at it at blistering speed. But an engine is useless without fuel. Where do they get enough data to make this savant network actually smart? Because training a 5 billion connection model on a few hours of audio is going to lead nowhere.
To train a model of this scale, you need a staggering, unprecedented amount of data, and they gathered everything they could get their hands on.
Like what?
They used the Wall Street Journal dataset, which is about 80 hours of high-quality read speech. They used Switchboard, which is roughly 300 hours of conversational telephone speech. They incorporated the Fisher dataset, a massive 2,000 hours of conversational data.
A whole lot.
And then Baidu utilized their own proprietary data set of read speech, which was another 5,000 hours.
So we are looking at roughly 7,000 to 8,000 hours of audio.
Yeah.
That's a massive corpus. But there is a glaring catch here, isn't there?
What's the catch?
The whole thesis of this paper is that end-to-end models conquer noisy environments. But the data sets you just listed, Wall Street Journal readings, clean telephone calls, that's mostly clean audio.
Ah, yes.
If you train this massive neural network in a perfectly quiet digital room, it is going to panic the second it hears a siren or a coffee grinder in the real world.
Exactly. A model is only as robust as its training data. If it never hears a siren during training, it won't know how to ignore one during testing.
But logistically, capturing thousands of hours of perfectly transcribed data in naturally chaotic environments, like a crowded cafeteria, a subway station, or a moving car in the rain, is impossible. You can't send thousands of actors into a hurricane to read the Wall Street Journal.
You can't. So the Baidu team had to synthesize the chaos. They used a technique called synthesis by superposition.
Which sounds incredibly technical, but at its core, it just means layering sounds on top of each other, right? Taking a clean vocal track and pasting a track of a barking dog over it.
At its core, yes. But the way they executed it is what separates a good model from a great one. The naive approach to synthesis is to just download a 10-hour track of white noise from YouTube and digitally loop it over your entire clean speech data set.
What's wrong with that? It adds noise.
Because neural networks are lazy and they are incredibly smart at finding shortcuts. If you use a single looping noise track, the network won't actually learn to understand speech better.
What does it learn instead?
It will memorize the exact frequency pattern of that specific white noise track and simply apply a digital subtraction filter to remove it. It learns a parlor trick. It learns to recognize that one specific noise rather than learning true, generalized robustness.
So the network is basically cheating on the test.
Yeah.
It's saying, oh, I recognize the exact hum of this specific refrigerator motor. I'll just delete those frequencies. But the second it hears a different refrigerator, it fails.
Precisely. To prevent the network from cheating, the Baidu researchers had to make the noise unpredictable.
How did they do that?
They collected thousands of very short, distinct audio clips to act as noise sources. A snippet of a TV commercial, a few seconds of a dishwasher running, the clatter of plates in a cafeteria.
Right.
And they superimposed many of these short clips randomly over the clean speech. The background noise was constantly shifting, chaotic, and completely unpredictable.
So it couldn't memorize it.
Right. The network was forced to learn the harder underlying task, actively listening to the human voice through whatever chaos was happening around it.
Okay, that is clever engineering. But I have to say, my absolute favorite part of this entire paper, the highlight of this section for me, is what comes next. Because adding digital noise over a clean recording has a fundamental biological flaw.
Yeah.
And the researchers recognized it.
It is a phenomenal cross-disciplinary insight.
Right. Think about how you act in the real world. If you are sitting in a perfectly quiet room reading a book out loud, your vocal cords are relaxed. Your pitch is steady.
Yeah.
But if you are in a crowded bar and the music is blaring, you don't just speak normally while noise happens around you. You involuntarily change. You raise your pitch. You change your inflection. You yell a little bit.
You strain.
Exactly. You over-enunciate certain consonants to punch through the music. That involuntary biological change in human speech in response to a loud environment is a documented phenomenon. It is called the Lombard Effect.
And this is the critical flaw in simple data synthesis. You cannot simulate the Lombard effect in digital post-production. You cannot take a recording of a relaxed person in a quiet room, apply an audio filter, and make them sound like they are straining to talk over a loud TV.
Because the physics are wrong.
Right. The physical mechanics of their chest, their throat, their vocal cords, it all changes in the moment. The acoustic properties of the speech itself are fundamentally different.
So how do you capture that biological data without actually recording in a noisy bar, which would ruin the clean microphone feed?
It's so cool.
The Baidu team's solution is so elegant. They put human subjects in a perfectly soundproof, quiet room. They put a high-quality microphone in front of them, and then they put headphones on the subjects and blasted incredibly loud background noise directly into their ears.
It is genius. The humans instinctively, subconsciously compensated for the loud noise they were hearing in their headphones. They strained their voices, they altered their pitch, they exhibited the exact physiological traits of the Lombard effect.
But the microphone only captured their voice. It didn't capture the noise because the noise was contained inside the headphones.
Exactly. They captured the raw, biological human response to noise, completely isolated from the noise itself. This gave them perfectly clean audio of someone speaking as if they were in a loud room. And then, in post-production, they could digitally superimpose whatever background noise they wanted over that strained audio.
I just marvel at the psychological cleverness of this. It bridges the gap between digital data synthesis and human behavioral psychology. It shows a profound understanding that speech isn't just an acoustic signal moving through the air. It is a behavioral output deeply modified by the environment.
It really is a beautiful piece of experimental design. It ensured that their synthesized data set wasn't just acoustically noisy, but biologically accurate.
Okay, so the model has it all. It has the biologically accurate chaotic data. It has the hardware tunnels. It has the clipped ReLU architecture. The training finishes. The model is baked. So what happens when we unleash this end-to-end savant? What happens when an RNN tries to spell English words purely based on sound, without any linguistic rules to guide it?
Well, it gets a little phonetically confused.
It spells like a kindergartner. This is where we need to talk about the paper's blind spots and the reliance on language models. The raw output of this incredibly advanced neural network is fascinating, but grammatically, it is a disaster.
The authors are very transparent about this in the paper, and they give some great examples. The RNN would transcribe a sentence like, "What is the weather like in Boston?" But it would spell Boston as Bostin. Or for the name Narendra Modi, it would output Narendra Modi.
Boston, I mean, it makes perfect phonetic sense. If you just sound it out, that is exactly what it sounds like. But it is obviously grammatically wrong.
It highlights the limitation of the pure end-to-end acoustic approach. The RNN only knows the physics of the sound. It has never read a book. It has never seen a dictionary.
It doesn't know spelling.
Right. It doesn't know that Boston is a proper noun spelled with an O. To fix this, the researchers had to admit that pure acoustics wasn't enough. They had to bolt on a traditional language model during the final decoding phase to act as a spell checker.
They created a specific objective function to balance what the acoustic RNN heard with what the traditional language model knows. Let's look at how that balancing act works. I don't want to read the equation, but how do these two systems argue with each other to decide the final spelling?
Think of it as a weighted voting system. You have the RNN, which is analyzing the audio. The RNN votes and says, based on the acoustic wave, I am highly confident the letters are Bostin.
That's the acoustic probability.
Right. But then you have the language model. The researchers used a massive n-gram language model for this.
Let's clarify what an n-gram model is for our listeners. It's not a neural network, right?
No, it's essentially a massive statistical lookup table. An n-gram model analyzes vast amounts of text and calculates the probability of words or letters appearing next to each other.
Yeah.
The model they used was trained on 220 million phrases with a vocabulary of nearly 500,000 words. So the language model looks at the sequence Bostin and says, wait a minute, I have read 220 million English phrases, and that sequence of letters has a statistically near zero probability of occurring. However, the sequence Boston occurs constantly.
So the language model vetoes the acoustic model.
Exactly. The final objective function scales these two opinions against each other. It combines the RNN's acoustic confidence with the language model's statistical probability. It also adds a third term, a word count penalty.
Why word count penalty?
Because without it, the system might try to maximize probability by either guessing one massive run-on nonsense word or by chopping the audio up into 100 tiny, high-probability one-letter words like A and I. The word count parameter forces the system to find a natural sentence structure.
And how does it navigate all these thousands of possible spellings to find the best one? Does it calculate every single permutation?
That would take too long. We use an algorithm called a beam search.
What's a beam search?
Imagine you are in a maze looking for the exit. At every fork in the road, you clone yourself and send a clone down each path. But to prevent having a billion clones, you only keep the, say, 1,000 clones who seem closest to the exit, and you kill off the rest.
Okay, that makes sense.
The beam search explores thousands of possible character sequences simultaneously, continuously pruning the lowest probability paths until it finds the single sequence that maximizes the combined score of the RNN and the language model.
I think it's important to pause here and acknowledge this as the paper's primary blind spot. This paper is heralded as the triumphs of end-to-end deep learning, the idea that we throw away the hand-engineered pipelines.
Right.
But the reality is they didn't throw it all away. They still desperately needed this massive, statistically rigid n-gram text model strapped to the back of the RNN to make the output legible. Without the traditional language model holding its hand, the end-to-end system failed at basic spelling.
That is a very valid critique.
Yeah.
It was a massive leap forward, but it wasn't a pure, unadulterated victory for solely neural architectures. And the spelling wasn't their only problem. The authors also explicitly admitted that their massive RNN was highly prone to overfitting.
Overfitting meaning the network was just memorizing the training data instead of learning the general rules of speech.
Precisely. Even with 7,000 hours of audio and chaotic synthesized noise, a 5 billion connection network has enough internal memory to just memorize specific clips.
So it's not actually learning.
Right. If it hears the same Wall Street Journal reading twice, it stops listening to the acoustics and just regurgitates the text from memory. When you test it on new unseen audio, it fails.
So how did they force it to generalize? How do you stop a savant from just memorizing the textbook?
They employed a barrage of regularization techniques. First, they used dropout. In the feed-forward layers, they literally turned off 5% to 10% of the neurons completely randomly during every pass of training.
That sounds counterproductive. Why turn off the brain cells you just built?
Because it prevents reliance. If a specific cluster of neurons starts memorizing a specific audio clip, turning them off forces the rest of the network to pick up the slack.
Oh, I see.
It forces the network to distribute the learning widely, creating redundant, robust pathways rather than brittle, localized memories.
It's like forcing a sports team to practice while randomly blindfolding different players. The team has to learn to communicate better overall, rather than just relying on their star player every time.
Exactly. They also used ensembling. They trained multiple slightly different versions of the deep speech network independently, and then averaged their predictions together at the end. The mistakes of one network cancel out the mistakes of another.
And there was one more trick they used to fight overfitting, something called jittering. Explain jittering, because when I read it, it sounded like a desperate hack, but clearly it works.
It is a classic machine learning trick adapted for audio. In image recognition, if you want to stop a network from memorizing a picture of a cat, you might shift the image 2 pixels to the left, or rotate it slightly.
Okay.
The cat is still there, but the raw data numbers are different. The Baidu team applied this to time series audio.
They shifted the time.
Yes. During training, they would take the raw audio file and literally translate it 5 milliseconds to the left and then 5 milliseconds to the right.
So they are slightly misaligning the audio with the time steps.
Right. It forces the network to realize that the exact specific millisecond a sound starts doesn't matter. The absolute timing is irrelevant. It's the relative pattern of the frequencies that matters.
That's really clever.
Shifting the audio acts as a massive variance reducer. It creates artificially new data points from the existing audio, making it much harder for the network to memorize specific timestamps.
Okay, so they have the bidirectional RNN. They've strapped the n-gram language model to the back of it to fix the spelling. They've randomly dropped out neurons, ensembled the models, and jittered the audio back and forth in time to prevent memorization.
That's the recipe.
After all of this incredible engineering, it is time for the final test. The showdown. Let's look at the actual experimental result and the lasting impact of this paper. Did this blunt force deep learning approach actually beat the highly refined, decades-old Rube Goldberg machines?
It absolutely smashed them. The numbers in the paper are historic. Let's look at the primary benchmark they used. the Switchboard Hub5 Cyril test. This was the gold standard in the academic community for evaluating conversational speech recognition. It was notoriously difficult.
What was the reigning champion before deep speech?
The previous best result was published by Vensley et al. They used a highly complex, deeply tuned DNN-HMM hybrid model. It was the absolute pinnacle of the old paradigm. That model achieved a word error rate, or WER, of 18.4%, meaning it got roughly 18 out of every 100 words wrong.
And what did deep speech achieve?
Deep speech achieved a 16.0% word error rate.
A 2.4% drop. Now, to a layperson, dropping from 18 to 16 might not sound like a revolution. But in a field where entire PhDs are dedicated to fighting for a 0.1% improvement, a 2.4% drop is an earthquake.
It was a monumental leap forward. It proved that the end-to-end approach wasn't just viable, it was superior. But remember, the switchboard test is relatively clean audio. The true test of their thesis, the reason they did all that Lombard Effect synthesis, was the noise test.
Right. How did it do when the sirens started blaring?
The researchers created a custom noisy speech test. They took 100 clean audio clips and superimposed loud background noise washing dishes, crowded cafeterias, cars driving in the rain. They set the signal-to-noise ratio to a brutal 2 to 6 decibels, which means the background noise was almost as loud as the speaker.
And they didn't just test it against academic papers. They tested it against the absolute best commercial APIs available on the market at that exact moment in 2014.
Let's read the scoreboard for this noisy test. Apple dictation achieved a 26.73% word error rate. Over a quarter of the words were wrong.
Wow.
Bing speech was slightly better at 22.05%. The Google API, which was considered top tier, was at 16.72%.
And where did deep speech land?
Deep speech crushed every single one of them with an 11.85% combined word error rate.
11.85%, almost a full 5-point gap between them and Google's multi-billion-dollar API. That is staggering. It wasn't just an academic victory, it was a total commercial humiliation for the old methods. And did they run an ablation study to prove that their specific noise synthesis trick was the reason they won?
Yes, they did, and the ablation study is definitive proof. When they trained the exact same deep speech network without the chaotic synthesized noise, its error rate on the noisy test was a dismal 28.7%.
Oh, wow. So it was worse than Apple.
Worse than Apple. But the moment they trained it with the synthesized noise, the error dropped to that 22.6% mark on a specific subtest. The technique demonstrably, unequivocally worked.
If we step back and connect this to the bigger picture of machine learning history, what they proved here was deeply controversial. They proved that a radically simple architecture, armed with massive amounts of data and brutal computing power, will fundamentally outperform a complex, elegantly hand-engineered model that relies on human logic.
It is the ultimate confirmation of Richard Sutton's famous essay, The Bitter Lesson. The bitter lesson of AI research is that trying to build human knowledge into an AI system only helps in the short term. In the long run, general methods that leverage massive computation like search and learning always win. The Baidu team proved the bitter lesson applied to speech.
So looking back from where we are today, I have to ask a legacy question. Did this specific network architecture, the clipped ReLUs, the striding, the bidirectional recurrent layers, did that exact structure win out in the long run? Is that what is running inside my phone today?
The short answer is no. The specific architecture they used here is largely obsolete today. The field of deep learning moves too fast. Today, state-of-the-art speech systems do not use basic ReLUs and recurrent layers.
What replaced them?
Transformers. The attention mechanism revolutionized sequence modeling. Modern systems use massive transformer architectures, or conformer models, which blend convolutions with self-attention.
How is that different?
Well, they don't process time sequentially like an RNN. They look at the entire sequence at once, identifying relationships between words regardless of how far apart they are.
So the technology evolved, but the soul of the paper.
The soul of the paper became the foundation of modern AI. The core philosophy of deep speech mapping raw audio directly to text at massive scale, entirely bypassing phone dictionaries, acoustic models, and linguistic feature extractors, that became the undisputed industry standard.
Yeah.
They proved that end-to-end learning was the future. They proved you could trust the neural network to figure out the physics and the linguistics on its own, provided you gave it enough compute and enough data.
Which is an incredible legacy to leave behind. They smashed the Rube Goldberg machine, and nobody ever tried to put it back together. Okay, we have covered the history of the field, the intricacies of the math, the brilliant hardware engineering, the psychology of the data, and the historic results. It is time to take these core concepts and extrapolate them into the future. It is time for our final segment.
The Novel Notions segment.
Exactly. And to our listeners, let me give you the standard, highly necessary disclaimer. The following segment is purely speculative. It is for entertainment purposes only. We are not citing the paper anymore. We are pitching outlandish, slightly crazy, but logically consistent research ideas based purely on the mechanics we just discussed. So grab your lab coats. Let's get weird. What is your first idea?
I'll let you lead off. What have you got?
Okay, idea one. I am calling it synthetic behavioral distortion for LLMs. This is directly inspired by the most fascinating part of the paper for me, how they captured the Lombard effect.
Okay, the biological response to noise.
Right. Remember, they didn't just add digital noise. They blasted loud noise into the human speaker's ears to force a biological behavioral compensation in the source data itself.
The psychological trick to force robustness.
Right. So what if we apply that exact same philosophy to foundational large language models? Right now, when we train an LLM to write code or solve math, we feed it perfect, clean data. We give it highly upvoted code from GitHub. Or maybe, at best, we give it code with a few syntax errors to teach it basic debugging. But the environment is sterile. What if we alter the environment of the data generation?
How do you induce a psychological state of stress in a language model during training? It doesn't have vocal cords to strain.
By actively injecting stress prompts or simulating severely restrictive compute constraints in the meta-prompting layer during the synthetic data generation phase.
Okay, I'm listening.
Imagine we have a massive teacher model generating a data set of Python code. But during the generation process, we constantly randomly interrupt it with adversarial prompts. Urgent. You only have 500 kilobytes of memory left. Or, warning. The database API you are calling just deprecated half its endpoints. Rewrite instantly.
You are forcing the model to generate a data set of highly defensive code.
Yes. You force the teacher model to write defensively structured paranoid outputs. It starts adding massive error handling loops. It stops relying on external libraries. Instead of just adding digital noise to the final text, you dynamically alter the environment of the text generation.
That's really interesting.
You capture the AI's behavioral compensation. You'd end up with a data set that trains a natively paranoid, incredibly resilient model, much like a human's training to ensure they are understood over a loud siren. The experiment would be taking a base model, fine-tuning it on this stressed synthetic data set, and seeing if its zero-shot performance on complex, messy, real-world legacy code bases improves compared to a model trained on perfectly clean code.
That is deeply fascinating. It shifts the paradigm of data augmentation. Instead of augmenting the output data, you are augmenting the state of the agent generating the data. It's inducing algorithmic anxiety. I like that a lot.
All right, your turn. What is idea two?
I am calling my idea time-split context battens. This is directly inspired by their incredible hardware hack, the T202 midpoint swap across the GPUs. Remember the tunnel digging analogy? Slicing the recurrent network in half to avoid massive motherboard data transfers.
Meeting in the middle of the mountain to pass the blueprints, yes.
Could we apply this exact topography to modern LLMs that are currently choking on massive context windows? Right now, the entire industry is racing to build models that can process millions, even billions of tokens. They want an LLM to ingest an entire massive code base or a library of books in a single prompt.
But the memory requirements for that are astronomical.
Exactly. Holding an entire million token sequence in the VRAM of a single GPU, or even a synchronized cluster, creates an immense memory and communication bottleneck. The attention mechanism requires calculating the relationship between every token and every other token. It scales quadratically.
Right.
It's why long context models are so wildly expensive and slow to run.
So how do we dig a tunnel through a million tokens?
Instead of trying to hold the entire massive sequence in memory at once, what if we use a highly decentralized grid of very cheap GPUs? Let's say we have a 1,000,000 token document. We break it into 100 sequential chunks of 10,000 tokens each. GPU 1 gets chunk 1, GPU 2 gets chunk 2 all the way to GPU 100.
They process their chunks completely simultaneously.
Yes, in total isolation. They process their local 10,000 tokens, computing forward context vectors and backward context vectors internally, just like the bidirectional RNN. But here's the trick. At the exact midpoint of their respective chunks, they pause. They pass a highly compressed context baton, a vector summary of their chunk, to their immediate neighbors on the grid.
They exchange activations.
In a synchronized, rippling wave across the entire hardware network, GPU 50 hands its forward baton to 51 and its backward baton to 49. They integrate the neighbor's baton into their local attention mechanism and finish processing their chunk. You effectively create an infinite context window that ripples across decentralized cheap hardware. No single central processor ever has to hold the entire million token sequence at once.
Oh, that's brilliant. It's temporal model parallelism taken to a hyper-decentralized extreme. You are mapping the chronological flow of time in the text directly to the physical layout of the GPU cluster. You could theoretically process a billion token context window if you had enough cheap consumer graphics cards just passing the state batons back and forth like a bucket brigade.
Exactly. You eliminate the central memory bottleneck entirely by treating the context as a physical wave moving through a decentralized grid.
That is a phenomenal notion. And it shows just how much we can still learn from the raw engineering hacks of the early deep learning pioneers. And that brings us to the end of our deep dive. To you, listening right now, thank you for joining us on this highly technical journey through the incredibly muddy waters of early speech recognition. We started this deep dive talking about the frustration of rigid, hand-engineered systems, the digital cochleas, and the phoneme rulebooks that fell apart the second the real world got loud.
And we saw how the Baidu team systematically dismantled that entire paradigm. They abandoned the false precision of linguistics, and they embraced the messy, chaotic reality of raw sound waves.
They built an engine out of basic ReLUs, they hacked their GPUs to dig tunnels through time, and they fundamentally changed how computers interact with human voices forever. The link to the deep speech paper is in the bio. We highly encourage you to go read it, ponder those novel notions, and think about the rigid rules in your own field.
Until next time.
Keep diving deep. But before we go, I want to leave you with one final thought to mull over. We talked extensively today about how deep speech bypassed human phones because the neural network found its own, more mathematically efficient way to categorize sound. Makes you wonder if end-to-end models continue to evolve, talking to each other across vast networks. Will they eventually invent an entirely new phonetic structure? A hyper-compressed, highly robust vocal language designed purely for machines, utterly unrecognizable to the human ear. And if they do, how long until we try to learn it? See you next time.